All right, so this little lecture will be about sound, which is a particular kind of wave. Sound is a longitudinal wave, which means that its compression is in the direction of movement. Okay, so it creates areas of low pressure and high pressure in the direction of the wave as it moves through space. And here we can see an image of that, right? So you have areas, say, of high pressure here and of low pressure there. And that hits your eardrum, and then it moves your eardrum, right? Your eardrum, like if you have a high pressure wave, part of the wave here, and lower pressure here, it's going to compress that that eardrum. And so the eardrum picks up the frequency and the amplitude of the wave. Pitch is our perception of frequency. So we hear low frequency as low sounds, what we call low sounds, and high frequency as high sounds. And most sound wave is really quite complex. So you don't see a nice sinusoidal wave here. You see something like this with a sound wave. And what that means is it's combining a whole bunch of different frequencies into a single wave. So these frequencies are all added on top of each other. And so here we can see an image of a particular note being played on a clarinet. And you can see that you have the primary or the fundamental frequency here, right? And then these are overtones, right? So this is 231 hertz. This is 3 times that, 693. 1155 is what? 5 times the fundamental. So it's your first, your third, and your fifth, and your seventh fundamental frequencies. And these variations and the little things going on in between here, this is what makes things sound like what they sound like. And Joe's voice sounds like Joe's voice, and Sue's voice sounds like Sue's voice, and a clarinet sounds like a clarinet and not a trumpet. The human ear can detect tones in a huge range of frequency, from 20 hertz all the way up to about 20,000 hertz. The amplitude of a wave, that is how much it's oscillating, is related to its intensity. And the intensity is the power of the individual disturbance divided by the area through which the wave has spread. Okay, so the power comes from the source, right? We might have a speaker here, and so it's producing a certain wave of a certain amplitude. But as the wave moves out into space, this wave here has the same amount of power as this wave here. But this outside wave is clearly much larger. So the same power is spread out over a larger area, which means that intensity of the sound goes down as you move away from the source. Okay, so we have the power, which has to do with the source, and the area through which that wave has spread, which has to do, if it moves in a sphere or a circle, has to do with the radius. This is the equation for a sphere, essentially, for the area of the sphere. So the total power of the wave stays the same, that's P, but the intensity diminishes with distance from the source. And over here you can see some of that range of human hearing, right? So here are, at different frequencies, the lowest intensity wave that humans can detect. So we detect best at here in this range. And here is where it starts to actually hurt. You saw on that plot last time intensity on one bar and decibels on the other. And decibels are a little tricky because it's a logarithmic scale, and it's a logarithmic scale multiplied by 10. Okay, so with each step up by an order of magnitude of intensity from 10 to the 11th to 10 to the 10th, or to the 10 to the negative 11th to 10 to the negative 10th. That's, in other words, this has 10 times more intensity than this. It goes up by one step from 1 to 2, but then that's multiplied by 10. So every step up 10 on the decibel scale means an order of magnitude increase in intensity. So how much more intense is a 100 decibel noise compared to a 70 decibel noise? 3 orders of magnitude, which is 1,000 times, right? It's the difference between 10 to the negative 2 and 10 to the negative 5th. So yeah, that's just what I was saying here before.